Okay, I think maybe I'm successfully recording. Haven't done it since we left last term, so who knows? Alrighty, guys. Don't forget, welcome to physics. You need your physics book. You probably will want your formula and data book, and you will very likely want a pen or pencil and a calculator as well. All right. Last lesson, we got introduced to this idea of electrostatics, this attractive and repulsive phenomenon that occurs between things that generate electric fields, electrically charged things. They can be positive, they can be negative, they behave in different ways depending on whether they're positive or negative. Do we totally understand it? No, very much not so. All we know is that if you take two things that have this property of electricity or something, and you put them near each other, if they're the same charge, they repel. If they're opposite charge, they attract. Okay? Some pretty complicated situations can come up from this. We looked at a very simple one last lesson where we had two negative charges. We had a positive and a negative charge side by side. They attract each other with a certain amount of force. We know the exact formulas that give us the exact force, and we can predict from that force how fast they'll accelerate. F equals ma works perfectly here. We can easily predict the motion of these particles, which is pretty cool. What we want to move on to, though, is a much more complex situation. So let's do a little bit more difficult of an example. Let's do, in your textbook, this is work example 6.1. B. Can I? Is this a thing I can do? Hang on. Hang on. Hold your thought. Nope, turns out you can't. Never mind. All right, sorry. I was just experimenting with something there while you relaxed. Keyboard. Just decided if I'm going to do physics, I'm going to be comfortable. They're fake. Sorry. I'll get quicker at this, I swear. Okie dokie. Write this down. I don't know the shortcuts on an Apple keyboard. Switch back to the pencil. I know I said from left to right, but then I couldn't fit it, and now I'm writing it downwards. No, I'll write it in a line. Yeah. QB is a negative 10. And QC equals positive 10. And they are also arranged in that order like this. Whoop, that's an oval. There we go. This one's QA, this one's QB, This one's QC. We know the charge is up the top. They are separated by the following distance. Oops. This is 100. Obviously, not drawn to scale. And the question continues to say, because I thought I'd try something different. I think you're right. But it's also because I often, quite regularly, change the question from the textbook a little bit in various ways. So let's bump up that font size. Why is that not working? Okay, makes sense? So slightly more complicated situation, but really nothing crazy, all right? What's interesting, though, is the language in that question, okay? So let's very quickly talk specifically about this part here. Please. Right? That's what's interesting about this language. We learnt with the last example that the forces are going to be equal and opposite, okay? But that doesn't mean that all the charges are always going to experience the exact same force, because in some cases, in this case, for example, charge B is going to experience a significant effect from the electric fields of QA and QC. So its forces will be significantly affected by that. QA's effect on QC is significantly reduced. Why? Further away. Further away, so QA won't feel the effects of QC in the same way that QB will. So the forces can be different, okay? Now, the question specifies calculate the net force on B due to A and C, okay? There's really simple ways of doing this. There's really complicated ways of doing this. I tend to just write about the thing we're focused on and its experience. So when we notate here, this question, we can interpret it to mean find force B, the force that B experiences from all other charges, okay? Now to do that, we're going to find the force that B experiences due to charge A, and then the force that B experiences due to charge C, and then obviously take the sum of those vector quantities because we are dealing with vectors here. Force is a vector, of course, so we're going to do some vector addition. Thankfully, because we're still just in sort of a one-dimensional line, things will be pretty straightforward. It'll just be plus or minus based off whether it's going left or right. Make sense? Yeah. So we could establish our little, as we often do with lots of different types of problems, to the right is positive, to the left is negative. Okay, get a bit of a frame of reference going just to get the ball rolling here. Okay, so let's find the force that B experiences due to A. Is this easy enough to see? Is that okay, that color? All right, go do this, except with B and A. You've got your example from last lesson where we were looking at the effects of a force from two charges. Go do that now for B and A. Then do it for the force on B from C. and then find the sum. Reckon you just could do that without too much from me? Okay, get stuck into it, I'll roam around. Oh, sorry, yeah. Blank pages and help you, is it? Okay, let's look at the answer. Some people might not be finished, but hopefully you've had enough time to get through it enough that you get it. Now, if you're about to copy this down, we're going to have a discussion about this little notation in a second. So if you're going to copy down what I'm writing now, just leave a bit of space after that B, and we're going to have a little chat. Force on B from A, force on B equals 0.90. Yeah, because we had microcoulombs by 10 to the negative 6. Microcoulombs by 10 to the negative 6. And we had centimeters, which we needed to convert to meters. Negative or positive, that's a good point. I didn't actually check that. It's going to be QA is positive, QB is negative. The force on B is going to be negative to the left. So we should actually say negative, or in brackets, to the left. Remember, these are vectors. They're vector quantities. They have a direction. Sorry? Times by 10 to the negative 6. It's in your data book. Yep. Hey, quick point while we're on that, before I talk about the little notation comment I want to make. Because these two are attractive, right? Because we got a negative force out of it, we know that they're attractive, they're pulling together. We can determine that the force on B, this little number down here that we just found, is going that way. That's pretty apparent, right? The force is going to pull it towards A because they're attracting. So we can say that that force is a negative value. And that's what I did here. I put the little negative number down here, right? Made it negative, yeah? Now, on this side, let's just talk about if that was the same situation, if they were attractive. And I'm drawing those arrows totally wrong, aren't I? Really, I should be saying arrows are like this because they're attractive. Now, I know in this case they are attractive, right? But I just want to make a point before we do it. That means the force, let me get rid of what we were talking about there. What does that mean about the force? It means that the force on B is that way. Now, when you calculate that force, because you've got a negative and a positive charge, you're going to get a negative answer, some negative number, okay, negative K, let's call it. That just means that the force is attractive. It doesn't refer to our established frame of reference. It's a different negative there. That negative is just telling us it's an attractive force. We then need to say the force on B from C, that's on record, is to the right, and we set that to be positive. So when you then tell me FB equals something, you're going to give me a positive. Or you're going to say it's to the right, okay? If you're dealing with a case like this, where it's just two charges, attractive is usually enough, or repulsive, okay? But here we've set a reference frame, positive and negative. We'll get a negative or a positive answer. We need to use that to tell us the direction. It's not the be-all, end-all, okay? Especially because we're about to do it in 2 dimensions where you might get a force vector like this. You can't just say positive or negative. You need to give an exact direction. 30 degrees up from the horizontal, right? An exact direction. Those of you who are doing, was it methods? You had to do that assignment with vectors and you did polar coordinates and stuff. And unit vectors. All right. Is it specialist, is it? Anyway, doesn't matter. Point is, there's a bunch of different ways of giving me direction. If you're doing higher level math, you might see a couple of different ones. Okay, now let's talk about a problem here. Have a look at what's going on right here and tell me you found something that's going wrong and you also figured out a solution for when you were doing it in your book yourself. What's wrong with this? They're the exact same notation, but they're not the same thing, are they? No. So you can correct this any way you want. I just do f of b from a. F of b from c. And very shortly, f of b in total. Okay? That's probably the easiest. Some people chuck like weird arrows in there and stuff. I don't know what your textbook does. What does your textbook do? It appears to do what I do. Yeah. That's probably the easiest way. All right, let's get those answers then. So f of b from c, it will be attractive in this case. So the end result will be positive because it's going to go to the right. You should get a negative answer initially though, which is 3.6 newtons. 3.6 newtons, and initially again, that will be negative. You will identify that that means it's attractive, which means it will go to the right. That says to the right. Don't argue. I would rather you don't trust the negatives or positives. I would rather you trust the logic of like charges repel, opposite charges attract, and you figure it out from there. If you want, you could do all of this math with absolute values and then state your answer with a positive or negative at the end. Yep, welcome to. If you like the logic of including the negative on the charge when you do the calculation, and then if you get a negative answer in the end, you know it's attractive. If you like that, you can use that. But if you want to, you can do everything with absolute values here. It just means you don't have to think about it. You just do the to each other, because there's always two bodies involved. Same with gravity. This works with gravity as well. Yep. Okay, can I move on to the next page and we'll quickly chuck the total up there? Yep, so FB total equals the sum of all F on B, which equals 3.6 minus 0.9, yes? One's to the left, one's to the right. There's a difference there. We end up with 2.7 newtons. In which direction? We know it is because it's positive. In this case, the math actually does tell us. The negatives do tell us in accordance to our reference frame. To the right. But also, the charges are much closer. Those two charges, B and C, are much closer. And the charges on each of them are the same magnitude. They're all tens. So of course, C is going to have a greater effect on B. And if it's attractive, we can immediately tell. If this could be a multiple choice question, and you should be able to take one look at it and go, QB will go to the right. Because QC is much closer to it. The strength of that force will be much greater. It will be attractive because of the signs. I shouldn't need to give you any numbers, and you should be able to answer a multiple choice that's like, does it go to the left or the right? It goes to the right. Yes? And it is 4 times as strong, exactly. Yep, so 0.9 times by 4, 3.6. Yep. Cool? All right, let's do 2 dimensions. Yay, we're actually getting kind of realistic with it. Now, I'm not going to try and draw this one. I will actually take a photo of it. You guys annoying Campbell? Because you know he's my favorite student after last term when he did all his work. Oh, I'll go to a whole new page if that's okay with you guys. Uh-huh. Say that again, sir. All you need to know to answer that question is because r is squared, it's an inverse exponential. Does that ever reach 0? Technically, never. 0 is the asymptote. Okay. Same thing. The only difference is your forces, you're not just going to give me positive and negative directions and say blah, blah, blah. You are going to do degrees and trigonometry. The lines between the charges, let's highlight some key materials. So we know QA is positive 5 microcoulombs. QB is positive 5 microcoulombs. QC is negative 5. The separation distance is 5 centimeters, 5 centimeters, and 7.1 centimeters. So right angle triangle, says that there, 45 degrees. We want to calculate the force acting on charge object C. So what are we trying to find? What's our unknown that we want to find? Force acting on C. So force F on C is going to equal the force on C due to B plus the force on C due to A. Yeah? And they're all vector quantities. You can chuck your hats on now because we are definitely going to be using vector notation and stuff. Now, is C, the charge in question, attracted to A or repulsed? Attracted. Is C attracted to B or repulsed? Attracted. So it's attracted to both. Are B and A both the same magnitude of charge? Are they both the same distance away from C? So, based off that, you should be able to use a little bit of logic to determine a net force is going to look like this. Straight off the bat, right? You know for sure it's going straight up because it's an equal pull that way and an equal pull that way. So the net, the resultant vector is going to go straight up. It's going to do this. We're going to have a force going that way and then a force going that way, and that's going to be a right angle, and so we're going to end up straight up at the end. Adding vectors. You remember how to do this? Let's go figure it out. Hands up if you want me to go through this fully from start to finish myself, and you just copy. Okay, let's do that. Hannah, yep, I'm happy to do that. Give you a chance. Careful with your notation. Careful with your positives and negatives. Remember, a negative in the math just tells you it's attractive. You need to establish the direction. You can make assumptions about this. They don't actually specify, I don't think. You need to assume a coordinate grid of some sort where this line, this FAB line, is on a horizontal, okay? So you can assume some basic coordinate system there. Who can answer it? Max. Remember what we did with our fingers? Attractive, repulsed. A and B, which is code for repulsed. Okay. If you're going, you're on your own, you're doing it, great. Keep going. Don't stop. Don't stop me now. Is that what other people got? Negative 90 newtons for FCA? And then did a bunch of you waste your time doing FCB? FCB? Or did you all just go? Hands up, confess. Who wasted their time and actually manually calculated FCB separately? Charges are all exactly the same, distance is the same, you know for a fact it's the same. Next page. This is where things get funny. The total force on C equals the addition of FCA and FCB. How do we add vectors? Add vectors using what method? Yes, in what way? What do physicists do? We're nice and lazy, we just go tip to tail. Do it graphically. Remember, vectors are a graphical representation of something that otherwise doesn't exist visually. We visualize it. It's easy. You get FAC. That's what we have. And we know the angle. Oh, I've written them backwards. Sorry, I messed up my notation there. Let me correct that. Now we know that the FAC line has, it says interior angles of 45 degrees, so we can sort of, if you remember your Z rule, we could sort of make this conclusion. You could make it a bunch of different ways, geometrically speaking, but in physics, we're never going to give you super complicated, tricky trigonometry and stuff, so you can pretty safely assume that it's going to be easy numbers. So this one here is going to be 45 degrees, symmetrical, so 45 degrees, and you know that's a right angle. Just trust me. Is that fine? Right, but when we take this vector, oops, I just erased things. When we take this vector and we pop it there, we're basically equivalent of just rotating the whole triangle. This would be 45, this would be 45, we know it's 90. Yeah. C squared equals A squared plus B squared. Yep. Yeah, that's true. Yep, you don't even need to do trig. You can do Pythag. Yeah, you know the magnitude of C and B. You know it's a right angle triangle, so you know you can do Pythag. Let's do it that way, actually. That's definitely the quicker way. I'd almost forgotten about that too. So C squared equals A squared plus B squared. FC equals FCA plus FCB, each of them squared. Take the square root of that. If I lost you there because you haven't done Pythag in a while, I just took the square root of both sides. The square root of C squared just becomes C, but that C is this. So FC equals the square root of FCA was 90. They were both 90. I am going to totally ignore the negatives here, and you have to. Remember, the negatives were just to tell us the direction or the fact that it was attractive or repulsive. If we use them now, we'll get a negative number, and then we can't take the square root, and we'll be lost and scared. So 90 plus 90 squared, squared. 9 squared is 81, so is that 8,100? Which is 16,200, which the square root of that would be obviously, 197 point, sorry, 127 point what? Let's go 28. Yeah, that's fine. Either or. In what direction? Which way? Point. Everyone point. Straight up. Straight up. What else could you say instead of straight up? Polar. Someone said north, I think. Yep, that's one. Another one. True bearing. Zero degrees. North is 0 degrees on a true bearing, on a compass. Okay, ready to do it yourself properly? Are there any other challenges that I should discuss? I guess there's the challenge of when it repels, but I'll leave that to you guys. Didn't need to calculate what? FAD? Oh, FAB. We did FAB. FAB. No, sorry. Oh, did we? Did I write in the question to do both? Calculate the force acting on charged objects QC. So it just wanted the force acting on QC. Yeah. Okay, guys, let's do check your learning to make sure we have this. We're going to do start with question 5. It looks really big and long, but it's actually just 2 charges. Is it attractive? Is it repulsive? That's the first one. What's the magnitude of the force if distance r is doubled? It's actually not that bad. So start with question 5, then do question 6, which is multiple parts, and then question 7. That's so cruel. What when charges range on corners? Yeah, I'm gonna screenshot them and put them in a second. I am just deciding what else to give you. You've got 20 minutes. Should be able to get through those 2. Did I tell you I wasn't going to give you homework this week? We'll see, we'll see. What if I give you one question as homework? Because I don't think we're going to have time for it all today. When's your methods draft due? But if you just go to withdrawal room, it's due whenever the hell you feel like it? Is that? All right, well, what I'm getting at is if you don't get to it, question 9 is good. Skip questions 7 and 8. 8 is really fun, but I'm not going to force you to do it. I'll give you suggested questions here. Yeah, kind of. Well, my plan was to not give you homework this first week because I know some people are still doing those chapter reviews and trying to get them to me, but I'm going to give you one question, just one. So we're not doing chapter 2 and 5? Yeah, chapter 2 and 5. Oh yeah, I already gave you homework. When's it due? Chapter 2 and 5 is due by the time you do your external. Chapter 2 and 5 won't come up again probably until your external. There's some possibility of data test questions being within the context of 2 and 5, but the understandings of 2 and 5 probably not super important. Inclined planes and orbits. I mean, inclined planes just comes down to vector analysis anyway. Like, it's what we're doing right now anyway. Can I like snip in GoodNotes? Who's a GoodNotes expert? Can I snip in GoodNotes? Can I like, oh, I can use the lasso tool, can't I? Can I do a square lasso? I can't use the snipping tool, it's an iPad. Delete. No! What just happened? What? I'm on a computer. I'm on an iPad on a computer. No, but then I can't transfer that from that to this. I'd have to save it to the network. No, it's no. How about you just move it off the page and reset? No, my iPad is wirelessly projecting the screen to the computer. I should have stopped the recording. I can save this to my OneDrive. What are you doing right now? Yes. Question 5. So now I should be able to insert an image from my OneDrive. No, not that. Wait, you still need to see? What are you doing so vigorously over there, Max? This is a like, it's kind of fun, but maybe not. But these ones are definites. Definitely fun, but definitely do as well. Yeah, see, this is the issue. I've uploaded the image from my computer onto my OneDrive, but it hasn't uploaded yet. Oh, my OneDrive syncing is paused because I'm on low battery.